Today, we have the honor of inviting Professor Shukui Liu from Nanyang Technological University, Singapore, to talk on a very interesting method has been recently developed by him and his research group, and the method called SNNM method, and is a method, a semi-empirical method that can be used for different wave directions. So it's very, very interesting. This is a short bio of Dr. Shukui Liu. He's a lecturer actually at Nanyang Technological University, and also he's interested in ship hydrodynamics and dynamic problems, as well as their impacts on ship design and operation. And he's also a PI of a number of funded research projects, and he's author and co-author of over 40 scientific publications. And it's very interesting that his work has been adopted in IMO, International Maritime Organization guidelines, and International Time Conference, ITTC, recommended method. We are very happy that this method has been developed by Dr. Shukui Liu and his research group, and today we are going to talk about this method. This is also a short bio of me, and as I said, I'm also a PhD candidate in marine hydrodynamics and also an organizer of IMT webinars. Professor Shukui Liu, just feel free to share your screen and start your presentation. Thanks.
Okay, thank you, Exxon, for this very nice presentation, introduction. Okay, good morning, students, researchers, and professors from Norwegian University of Science and Technology. So this is Shukui from Nanyang Technological University. It is truly an honor of mine to be invited to present our research outcome on this semi-empirical approach to predict the eddy resistance of a ship in waves of arbitrary headings. So in today's talk, I will actually start with a review of the eddy resistance prediction methods, followed by the methodologies we adopted in developing the SNNM method. Thirdly, I'm going to share some validation results from the recent validation study carried out by ITTC SOS committee. And at last, I will draw some conclusions. So we know that the ships are operating in a very challenging and even harsh environment. The common environment conditions, including water, wind, and wave, particularly when wind drives water, a wave will be generated, and wave will interact with the ship. This will induce ship motions, and also there will be diffraction problems. All these will lead to the eddy resistance in waves. So for the eddy resistance in waves, let me use this simple scenario in towing tank to elaborate what exactly is the eddy resistance we are going to study. Just one moment. Okay, let me use this scenario in towing tank to show what eddy resistance is. So in towing tank, we would first measure the resistance in calm water, and we can get a curve. That is the calm water resistance. And then if we repeat it, the test in waves, then we may measure a second curve. And this curve is the resistance exerting on the ship in waves. So what we care about is this time average increase comparing to the resistance in calm water. We are not talking about the instantaneous difference. So it's the time average increase we care about. So for ships sailing in a seaway, the seaway normally is described by spectrum, Of course, in reality, when the ship sails in a seaway, the wave or the seaway condition comes from a certain direction, what we call it the primary wave direction. For this wave, there will be many elementary waves coming from random directions, all the directions actually. Depending on the scenario, there can be different angular distribution function employed to describe this situation. That being said, if the seaway condition can be described by directional spectrum, which include not only the frequency spectrum, but also the angular distribution, then the mean eddy resistance in the natural seaway can be calculated using this double integration. So that being said, given this frequency spectrum and angular distribution, and then we need to determine the eddy resistance for given ship speed, given arbitrary wave heading and arbitrary frequencies. So we need to have this transfer function to derive the mean eddy resistance in waves. So for the prediction of this RAW or this transfer function of eddy resistance in regular waves, there are actually quite a few methods available. As we see that this is essentially a sea-keeping problem. So all the methods that was developed for sea-keeping prediction can be used or can be extended to predict eddy resistance. Actually, this 27th ITTC Sea-Keeping Committee has reviewed all these methods and give a very thorough review on all these available methods. They can be roughly classified into 4 categories. The first one is the towing tank test. This is also regarded as the most reliable approach and serves as the yardstick for developing or validating various tools, numerical tools. So besides that, there will be also CFD methods and also potential flow methods, as well as some analytical or semi-empirical approaches. So at the moment, there are also some new methods, data-driven methods emerging. These are mostly in the primitive stage because of limitation of available data. So now let's talk about what is the state of art of eddy resistance prediction. To discuss this, let's first examine the quality or the state of art in the motion prediction. So here we have two very interesting graphs from the ITTC benchmark study. One was conducted in the late 70s, and one was 30 years later. Both were conducted for the standard S175 ship. So here is the most, maybe the easiest case for head waves. So in head waves, we predict the heave and pitch motion. As you can see, actually, there's quite some scattering in the for the motion for the prediction of the peak of the ships, and it seems that 30 years development didn't bring this this prediction to a more converged state. So it is not surprised that when we apply these methods to predict the eddy resistance, a more serious scattering was observed. So this graphs below shows the prediction of the eddy resistance of KVACC2 ship using various methods. This benchmark study was organized by Chopra project in 2016. So you can see actually not only in the peak region, but also in the short waves, high high frequency region. There's a lot of scattering. So considering of this situation, it seems that it will take a long time for all the methods to become to arrive at a more converged state, and probably a better approach would be to develop a transparent empirical approach to tackle this problem. So this was thinking we developed some years ago, and we started to work on this in the semi-empirical approach. And another point I like to highlight is that in practice, there are many scenarios that we do not even have the detailed how form to set up the model to run the advanced high fidelity simulations. For example, in early design stage, we do not have the how form yet. And also in practice for owners and operators, the most detailed information they may have is from this lines plan. So out of this lines plan to construct the model for simulation will actually induce further problems. Okay, so that being said, all of this lead us to consider of developing semi-empirical approaches. Besides, there were some urgent demands from the industry. So first of all, that time we were working on the minimum power propulsive power assessment problem. So that time there was a demand for semi-empirical approach, but there wasn't such. Secondly, there was also a demand from the speed correction in sea trial. It was very interesting that we got quite some, let's say, we were approached by both owners and designers complaining about the sea trial results. So that actually make us to further study this procedure, and we identify some further problems. A third subject actually is from this ship performance analysis, which is very of high interest at the moment. You can imagine for those for the data monitored on board of ships, actually these data are heavily polluted by the operational condition of the seaway in the seaway, and this data needs to be cleaned or processed before further treatment. So that is our motivation, and in the next I would start to elaborate how we develop this method. So first things first, here this brief timeline on the development of this method. So we started the development in the Shobera project in 2013. This project was coordinated by National Technological University of Athens. In the first stage, we developed the method from head waves to beam waves. And later on, from 2017 to 2020, we extended the method to arbitrary headings and validated and also validated. This work was done at the National Nanyang Technological University. And during this process, Marik China was supporting our development very actively. So at last, we named this method as SNNM method, just to acknowledge the contribution of this each consortium and institution. So a few words about the background of this developer team. Actually, at National Technological University of Athens, Professor Papanicolaou has already worked on this problem in the early 80s. And for me, myself, during my PhD study, I also worked on a far-field method to predict eddy resistance. And more recently, we have been focusing on the diffraction effect. So all these fundamental research provided us very useful tools to investigate the relationship between the Hall form, wave condition, and eddy resistance. Another important point is about the developer team's strong know-how in ship design. We know that, so here, this picture shows the book actually written by Professor Papanicolaou on ship design. Because of his strong background in hydrodynamics, he elaborated a lot the theory behind the ship design practice. So actually, I benefited a lot doing the translation of this book from to English and Chinese. So we worked a long time on that. Then when the time came, we need to work on a semi-empirical approach. The concept was sort of clear to me because I have been actually examining various empirical approaches in the translation work of this book. Another important point was this experimental database. Because we have worked for a long time on this subject, we could actually accumulate a lot of data, which was very useful and necessary for developing the semi-empirical approach. So this was the database we used at the time when we developed this method. It includes the data of more than 120 ships, more than 3,000 data points. So coming to the concept of the method itself, here this slide, actually this graph shows a typical graph for this row in head waves. So for predicting the eddy resistance, we actually follow the quite, let's say, traditional approach. So the total resistance, eddy resistance, is approximated by the reflection, by the summation of the reflection effect and motion effect. So for the reflection effect, we based on work on the method proposed by Professor Faultinson, and for the motion effect, using this based on the method proposed by Jenkins and Ferdinando in the 70s. So for the in the short waves, in the short waves, you can see actually the method of Professor Faultinson is mainly applied only for short waves, and for the reducing or motion effect, this empirical approach by Jenkins and Ferdinando can be applied. But neither method is let's say perfect. There were a lot of limitations of this method, considering the time and the specific task they were addressing when these methods were developed. So our work was actually to introduce more improvements and to introduce more corrections to make the formulas more versatile, so that they can deal with various scenarios. So in the following, I will be elaborating on how these improvements were introduced. So let's start from the reflection effect or diffraction effect. So for this part, the pioneering work is from Havelock, when he studied the drift force exerting on the wave breakers. He developed this formula, and then following that, Fuji and Takahashi they introduced two correcting factors. One is for the speed effect, one is for the reflection coefficient, for the reflection coefficient. This reflection coefficient was actually studied by many physicists. So the specific form was proposed by Arcel or Evans and Morris for different directions. Actually, it is a reflection coefficient when the wave is reflected by a thin barrier. And this approach was further improved by Takahashi and Tsujimoto, Italia in 2008. A third work was from Professor Paultinson in the 1980s. So he actually proposed a very elegant method which is applicable to arbitrary wave headings, and also the forward speed effect. The forward speed effect can also be accounted. In his work, the viscous effect and the diffraction effect from sharp corners were neglected. A fourth work is from Kohn in the 1982. He introduced three correction factors. One is for speed, one is scattering, or it is similar to this reflection coefficient. And another one, very interesting one, is the finite draft effect. So this was very interesting. What he said essentially is that when the wave, when the reflection phenomenon takes place, the reflected wave will only have impact on the structure from the free surface to the bottom. This is very correct. And also it was theoretically confirmed by Ogiwara in 1996. However, this finite draft effect was totally neglected by the following researchers. And the fifth work is from Sakamoto and Baba in 1986. In their work, their contribution is actually to make a small correction to this Paultinson's formula by introducing this cosine alpha. So this is more correct. Okay, then reviewing all this work, we proposed a physically more complete formula. It is based on the work of Professor Paultinson, but we introduce here this finite draft effect and reflection coefficient, as well as the contribution from the effect of the flare angle, the flare angle in the water on the waterline. Of course, we need to note that this reflection coefficient is not for a thin barrier. Instead, it is for a thick barrier, which is more ship-like. Okay, so there are many works devoted to this problem. What in our work we adopted the method proposed by Soy-Lemaitre and Gorin, and actually using this formula, we could predict very easily the drift force exerting on the on a barge here without using any panel, just using the water line, we can actually derive this this prediction, very satisfactory. For more general cases, particularly for ships, for fine ships sailing with forward speed, we would still need to introduce another factor to make empirical corrections, so that this formula can be applied to both full ships and fine ships at various speed. So in the next, we introduced some simplifications based on for this work for practical reasons. So in this simplification, the first thing we did was actually to use actually only 1 point or 2 points on the waterline. We introduce a length of entrance and length of run for the waterline. So by doing that, we can have two components calculating this added resistance due to diffraction effect, and so that we can avoid calculating this integral. So calculating integral is not a big issue, but in practice, very often we like the formula to be as transparent as possible and as easy as possible for the practicing engineers. Following that, we also need to address this, further simplify this draft correction, which include two terms. One is this 1 minus e to the power of negative 2 kd. This is the finite draft effect. Another one is this r squared. So you can see that this r squared, the calculation itself, requires a lot of effort. And in our approach, and in this graph, you can see that both terms, both items. So here the green, the blue curve is the R square, and the red curve is this finite draft effect. So if we multiply these two, we can get this navy curve. That is the curve we need to use when using this formula. But because we need to drop this R square, this blue curve in practice, what we did was to further tune this finite draft effect, this 1 minus exponential function. What we did was to actually set up a impose some condition for long waves at wavelength to ship length ratio 0.5. We let this red curve to become 0. So that you can see we can have this green curve. So we can have this green curve. This is with this we can form this alpha T star. Okay. So you see this expression is quite simple. We don't need to do any complicated calculations. It's just a exponential function, and then we can get this green curve. It's very close to this neighbor curve. So with that, we finished our work for the diffraction or reflection effect. So in the next, we are going to introduce these effects to which we introduced for the motion effects. So for ship in longer waves, wave may come from any direction. So the method of Jenkins-Ferdinander is working for head wave only. Okay. So we started also working on head waves, and by introducing more corrections. So in order to work on this formula, introduce improvements, let's first examine the structure of this formula by Jenkins-Ferdinander. So this is the original formula proposed by Jenkins-Ferdinander. So you can see in this formula, it starts with some ship particulars, and also there will be this A1, A2. Actually, they are depending on the loading condition of a ship and the speed of a ship. So as I've been said, given the particular scenario, all these blue parts are given values, and this function is actually essentially is a function of omega bar. So what is omega bar? So the expression of omega bar is actually it is a function of wave frequency multiplied by some function of ship length and pitch of radius of gyration for pitch and fruit number. So if this one can be plotted, this omega bar for a series of wave frequency, so we can get this curve, and then applying this function, okay, that is omega bar to the power of b1 and this exponential function, we can get this red curve. So you can see. Applying this function using B1 and D1, then we can get this this curve. So this is a very interesting point. Examining this curve, we can see the peak of this curve is at omega bar equals to 1. And this profile of the red curve is dependent on the value of B1 and D1. And then if we multiply this curve with this constant given here, we can get the added resistance due to motion effect. So that is the essence of the Jenkins-Ferdinander's formula. So in order to improve that, then we need to think. If we like to adjust the position of peak, then we need to adjust the omega bar. If we like to adjust this profile, then we need to adjust the B1 and D1. The same applies to the amplitude. If we like to adjust the amplitude, then we need to add some extra terms. So that is the structure. And the first work we did was actually to improve the formula for ship speed. More specifically, to have the formula work well for the low speed, because this was directly driven by the IMO developing the method for supporting the IMO guideline for minimum propulsive power assessment. So that for that work, mainly we are concerned at fruit numbers equal to 0.05 and even less. So we examined the performance of this omega function of omega bar. So when you see when this fruit number is extremely small, and following this expression, it would give us this red curve. Okay, so it's totally wrong. And the same applies to alpha 2, which is about the amplitude. So if we follow the original approach, that means that it will lead to the situation that at fruit number equal to 0, the amplitude will be 0. So these are not correct. So what we did was to use some data, experimental data and numerical generated data to get these omega bar values for this low speed range. And then we can introduce some simple expressions for this low speed range. So this is the first work we did. A second work was actually on the impact of ship type noted by block coefficient. In our application, early application, we noted that there was some slight mismatch from the prediction from actually experimental result, particularly for full ships. It's not surprising because the method of Jinke and Ferdinando was originally developed for fast cargo ships. So that gave us justification to collect more data regarding the added resistance at different fruit number, and we examined the location where the maximum value is observed. So we get this this plot. So you can see for this case, say for fruit number 0.15, and the location where the maximum maximum added resistance for full ships and for fine ships are quite different. So we further studied that. We did carry out numerical calculations, and we justified that this ship type impact in terms of block coefficient, and we introduced this block coefficient into the formula, so that this is actually can be viewed as a result of a data-driven approach. So we check the data and we identify the problem, and then we proposed a solution. So the next problem we studied was for the impact of main dimension ratios, given actually a situation of B over T, and when B over T systematically changes, we can actually predict the added resistance, and we can see that they follow specific trend. When B over T increases, both the amplitude and the location of the peak value changes towards certain direction. So if we pick out this value, and we can see that they follow certain trend at different speed, at different fruit number. And this actually, this can be captured by introducing some very simple functions based on this B over T value. So with this, we can actually extend the formula to be working for not only for standard B over T about 0.5 to 3, but also working for very high B over T values. It is important for ships in ballast condition and volume carriers. So the next, we studied also the impact of trade. So this is very important for ships and in ballast condition. So we collected the data for ships and the ballast condition at a certain speed, service speed about. Okay, we can see that all this data actually they scatter, they distribute very closely. Okay, it seems that they have their own specific pattern, and then we actually examined the difference between the original prediction and this experimental data. By examining the difference, we identified several correction factors, including the amplitude, as well as the this D1, so which is which is used to actually to calibrate this profile in longer wave in the longer waves. So that is our work for the impact of trim. So with that, so we extended, we finished our work extending the formula in head waves. In the following, in the next, we work on falling waves. So falling waves is a very tricky problem. Okay, here you can see a continuousship in falling waves, and with the continuousship features overhang. So this kind of feature is very difficult to capture for any type or any kind of numerical approach. For us, it was also very interesting point to work on. But remember that we have already a formula that is working at zero speed for in head waves. Okay, so for considering a 4 after symmetric Hall form, actually whether the wave comes from a head direction or from stern direction, it is the same from the hydrodynamic point of view for a symmetric ship. So this actually gives us the courage to apply the method for falling waves. So when we apply the original formula to study to predict the eddy resistance of bulk carrier at 0 speed in falling waves, and the agreement between this prediction and the experimental result was excellent. Remember that for short waves, we have already a formula which is valid for arbitrary directions and arbitrary speed. So our task then is reduced to work out for the radiation effect, how will this peak point will change with the increase of speed in falling waves. So that is our task. So actually, there were not much work working on the eddy resistance in falling waves. We didn't have much idea. However, we were inspired by by the concept when we examining this formula for diffraction problem. So examining this formula for diffraction for the resistance, eddy resistance due to diffraction. If we set this as 0, we can get the conclusion U equal to VG. So this is very interesting. That means when the ship speed equals to the group speed, then the eddy resistance due to diffraction is 0. So this is a very interesting point. It is in line with the fact that the energy of the wave is propagating at group velocity. So this gives us the reason to examine or to check the relative velocity between ship speed and wave velocity, whether it is group velocity or phase velocity. So from that point we could actually get our formula for falling waves. In any case, radiation problem, eddy resistance in falling waves due to radiation is very complicated. Okay, even when we consider a ship traveling at phase velocity, and assuming that the profile on ship does not change, but due to the fact that the wave energy will travel at group velocity, there will be still energy exchange between ship and wave. So that will still lead to eddy resistances. So we need to actually again turn to data. So we collected 5 sets of data for a few for different shapes. Actually, we have the data from 0 speed to a relatively higher speed. And out of examining each set of data, we could actually get some very interesting results, showing that we could figure out the relationship between ship speed and the frequency, okay, where the peak value is observed to become 0. Okay, that is by estimation. Okay, and these points actually are very close to the line that ship velocity is a quarter of celerity or a half of the wave group velocity. So this is a very important reference condition. Having this reference condition in mind, we could do the following. So when the fluid number is 0, ship speed is 0, we apply the original formula to calculate the eddy resistance in falling waves. And that case, it is a drift force pointing to the positive direction. It's eddy thrust. And when the ship speed is half of the group velocity, and due to our just following our conclusion, the reducing effect should be 0. This will give us the conclusion that the ship needs to consume a speed of half of the group velocity to escape from the drifting effect of the wave. Then if we give a ship an extra speed of half of the group velocity, then the eddy resistance exerting on the ship would be the same as if the ship were in head waves at 0 speed. So this is 0.3. So for whatever points between 0 speed and half of group velocity, or between half of the group velocity and group velocity, then we can apply linear interpolation. For even higher ship speed, then we can treat the scenario as if the ship were in head waves, but we apply this relative fluid number defined as u minus group velocity over the square root of GL. So with that, we get a solution for the eddy resistance in falling waves. So once we finish this step, actually what we can do is we can start working for other headings. For ball waves, we know that following this sea-keeping theory, we know that the resonance region will change with the frequency we encounter, and then we can calibrate this peak value also with this observed experimental data and numerical data. So we can get some simple functions to capture the change of the maximum value of the eddy resistance and its location. And for the stir oblique wave cases, okay, remember now we have extended the formula to beam wave case already. Okay, we can, because this value is in stern oblique waves is normally very small, so we can apply directly interpolation between beam case and falling wave case, so we can get this this result. So with that, we complete our methodology. Okay, so here is some comparison between predicted maximum values and the location where to expect them. So the first graph shows the maximum values for 3 ships at different speed, from 0 to moderate speed. And the second graph shows the location where this maximum value is observed. You can see actually for various headings, head waves to falling waves, we can have a very satisfactory agreement. So that means this the methodology proposed is very efficient. So with that, we can actually we have formed the whole formula, and for executing this formula, we need the input of 8 shape parameters: length, beam, and drafted forward, drafted aft, and block coefficients, and pitch radius of gyration of pitch, and 2 parameters of waterline. So with these 8 given parameters, shape parameters, we can generate the added resistance surface, okay, for arbitrary wave headings for any frequency. So by generating this surface, actually, okay, this was done in a MATLAB environment. It cost only about 10 to 15 seconds. If you do this calculation in Fortran, it will cost less than 1 second. So because the code is about 200 lines. On the other hand, to get this scattered experimental point, you know it's how much efforts we need and resources we need to devote. So after this development, we did some validation. This shows several cases for different headings and different speed and different loading conditions. You can find the details of these validation cases in our publication on ocean engineering. So in the next, I will use a few slides to share about the validation results at ITTC. So this method was first circulated to ITTC in the end of 2019 by invitation. And in January of 2020, I presented this method at the 4th meeting of this specialist committee. And then the validation work started in April. So after an extensive large-scale validation campaign, this method was finally accepted by ITTC by adopting it into this recommended procedure for C-trial, for analyzing the C-trial result in earlier this year in March. So here are the presentation of the data collected at this during this validation campaign. In total, the data of 29 ships, including 1,477 valid points, were used in the validation. And these data points, you can see the share of these data points as per ship type is actually a very good representation of the world fleet. You see a majority is for bulk carrier, gas carrier, and tankers, followed by container ships. And then there will be also for passenger ships. So these are, they can represent healthily the major ship types. In terms of data points for per wave heading, actually 30% about is for head waves, and for other headings, the share are quite evenly distributed. And this slide shows some selected results, particularly for falling or stern oblique wave conditions. Okay, these data of this validation result are from different organizations. You see here from Samsung, CSSRC, CTU, Marine, and HSVA. So these are really encouraging results, demonstrating that the proposed methodology for the falling, particularly for the falling wave condition, is efficient and is effective. So this slide shows the assessment result for the compulsory criteria that was set up by this SOS committee, saying that in order to be accepted by ITTC, the correlation coefficient R should be at least 0.78 for bow waves and 0.7 for other headings. And using this established database, the attained R for bow waves and other headings both are reached 0.86. There was also a voluntary criteria for assessing these relative errors for arbitrary headings. Actually, for these voluntary criteria, less data was contributed by the members, over 400 points. So out of this study, we can see that the scattering or the distribution of this relative error is evenly distributed. You can see the average value is merely negative 0.1%. And the distribution of this error has also a Gaussian feature with about 93% of samples within the range of 4%. So that says that this formula is very accurate. So there was also a face-to-face comparison with the enforced method, the StarWave 2. So we're using this same database. The StarWave 2 achieved a correlation coefficient of 0.7, and SNNM method achieved a value of 0.86. So with that, actually, the Advisory Council of ITTC approved the formula to be adopted by this ITTC recommended procedure for conducting the analysis of speed power trials. So that is openly that is available to public on the ITTC site. You can examine that. So with that, I've finished the development, the presentation on the development of this method. In the following, I will just draw some brief conclusions. So in this presentation, mainly I presented this development of this semi-empirical approach for the transparent prediction of eddy resistance in waves of arbitrary heading. And during this development, we conducted analytical analysis and parametric studies, and also some first principle investigations. And we also attuned the formula to a large experimental database. So the formula uses only 8 parameters as input and can deal with various scenarios. So that is very convenient for the for people in practice. And the formula was also validated by SOS committee with fully satisfactory result. So in the future, we are going to collect or generate more quality experimental data or CFD data to cover more shape types. And we are interested also to study more specific wave conditions, particularly for short waves and steep waves. So before completing this presentation, I'd like to acknowledge the contribution of this SOS committee for validating this method and for increasing our confidence in this method. So that is my presentation. So I shared more today about the methodology we adopted in developing this method. I hope this talk is useful for researchers working on the eddy resistance prediction, and also for the engineers implementing this method to their practical projects. Thank you very much for your attention.
Okay. Thank you very much, Dr. Liu, for a very nice presentation. We really enjoy it. And so anybody has a question, just feel free to ask it through the chat. And also, I can see that, yeah, I will also give you the chance to turn on your microphone and video to ask your question directly. Yeah. So I can see that Professor Swayze has a question. So feel free to turn on your microphone or video to ask your question.
Yes, thank you very much, Dr. Liu, for this very very nice presentation, giving me a much better understanding for how this method has evolved. It is indeed a significant step forward for practical calculations of added resistance. So I really think that this is an important contribution. You mentioned in your very introduction, in the early part of your introduction, that there is an increasing interest in using say big data and machine learning methods also in the field of added resistance. And in connection to that, I wonder if there has been any attempt at comparing the predictions by your method with the data from ships in operation. And the reason I'm asking is that from our research, we see that often there is you can have a good agreement between experiments and prediction. That means model experiments and prediction. While when you compare with the in-service data of ships, you often find large deviations in the direction of larger added resistance in practice. And
okay,
yeah, please.
Thank you, Professor Steen, for this very interesting question. Okay, I think I can share a little bit about my experience. You see, for the ships, for the measured or the monitored data on board of ships, normally we have a monitored power, and that is something mostly we have, okay? But from resistance to power, there are actually many steps involved in between. I don't think it is only the, of course, added resistance is a very important point, but there are also other factors affect a lot of in this power prediction. I think you have a rich work on this. I think maybe you know better than I do.
Yeah, you know that the model based in predictions, they are based on the correlation studies that actually use say sea trial data as the correction for the predictions from the model basin. So getting from measured power to resistance is a fairly well established practice.
Okay, I think the contribution of this work on added resistance is it can be used to reduce this scattering. Okay, we have some work on that. So if we apply some correction following this procedure, okay, various procedures available, we can really pre-process the data, the monitored data, to have a very good, let's say, process data. Based on that, we can follow up, continue our work. Okay, but I don't think it is only the added resistance play a role in this data treatment.
Sure, I agree to that. Thank you.
Thank you. Yeah.
And also, I can see that Professor Hai Min Khan also have a question. And feel free to turn on your microphone and video to ask your question.
Yes, thank you very much. Can you hear me okay?
Yeah, yes.
Thank you, Professor Liu, for a very nice presentation. I think it's really impressive work. And I just had a question about following Cs, because of course, at the end of the day, the model is based on experimental data mainly, or at least validated with experimental data in following Cs. And I know that it's very difficult actually to get accurate measurements of added resistance in following waves in the model tank. So I wonder what your thoughts are on what the status is of the quality of the actual experimental data in following waves.
Well, this is a very critical question. I try to share my views on this. Thank you, Professor Bingham, for this nice question. Okay. Actually, in the following waves, we have made some assumptions. Okay, so these are assumptions, and some assumptions that are even very difficult to validate, because one reference point is that at which point we will get the zero added resistance in following waves. So this is something I have considered many times, but I don't know actually how to efficiently validate this. However, when we compare these results really with available test data in falling waves and in stern oblique waves, this agreement is really encouraging. I'm sure that there should be much more efforts devoted to study on these scenarios, because this is a topic that very little effort has been, let's say, at least has been published.
Yeah, I agree absolutely, and I think one of my major criticisms about experimental data in our field is that you only very, very rarely find people who are making a good analysis of the experimental data, experimental uncertainties in their measurements. And I think this is what we are really critically lacking in this field, is because if you were to actually calculate the experimental uncertainties in your experiments and give that data as part of the experimental measurements, then you have the opportunity to see whether your whether your numerical calculations are actually within the uncertainty of the experiments or outside the uncertainty. But without that uncertainty analysis, it's very difficult to make any conclusions, I think.
I completely agree. I think this is some important work that maybe the token tanks can make more contributions.
Yes, I think so.
Unfortunately, we don't have that much data at hand. And also all the data we have at hand are mostly secondhand. So this makes uncertainty analysis more difficult.
Absolutely. Thank you very much.
Thank you, Professor. Yeah.
And okay, I also can see that there are some questions in the chat. Just a question from me. In the publication that you provide in 2020, you haven't mentioned the method as the SNNM method, and but in the 2021, in your publication, you mentioned that it is SNNM method. The method is completely similar to your last publication, or there is any updates in the method?
Thank you. This is a very important question. I like to take this opportunity to clarify. Essentially, they are the same method, okay? However, ITTC has their own system. For example, the one important difference is that in ITTC procedure, they define head wave as incident angle of angle 0. And in our method, we set it as 180. So when this method, when the method was adopted by ITTC, we rewrote the method to be in line with the ITTC system. But else, the essence is exactly the same.
Okay, thank you. And also, I can see Professor Apostolos Papanikolaou want to add some comments.
Hello, Shukui, and all the colleagues. I'd like to very briefly comment on the point that Professor Bingham brought up, because this is some tricky issue, as Shukui already mentioned. And in fact, he has shown in some slide earlier where we have experiments from Marine Tech, sorry, in this following wave case that is from the project Shopera, okay, where if you see these experiments and similar ones that we conducted also with other ships in the Shopera project, then you can say that, okay, any theory and any numerical approach and also experimental approach to capture this problem is actually very, very difficult, and how to approach it. In any case, you cannot expect that using some potential theory, a quasi a linear potential theory like we are using in panel methods and other related methods, that they can capture this kind of phenomenon. No? And in fact, the phenomenon is also very difficult to be captured also by a CFD code that could be also a reference, because the reference is for this SNNM method, and the data generation is not only by experiments, but it is also by numerical codes. And we've used that by our potential theory code, the new drift, and also CFD results beyond experimental results, where we have been lacking experiments. But in fact, the only thing you can do at the moment, at least, is to collect many data from following wave cases and see whether you can see some trends. And what Shukui has shown here is that we could capture some effect of this, so that the results look reasonable. I mean, else this formula as it is generated would fail. So that is, I think, an issue that many researchers will still investigate and publish. Although in practice, of course, this problem is in terms of regulations, EDI regulations, and other things that come for the determination of the powering and so on. The following waves case is not that important, like head waves case. That is the predominant case when you assess the powering and then the fuel consumption and the emissions of the ship, according to regulation. Thank you. Okay. And Shukui, very good job presenting.
Thank you, Professor. Thank you. And your supervision.
Yeah. Okay. Thank you very much for a very nice comment from Professor Apostolos Papanikolaou. And also, I can see there are some questions from Renato from Sinteb. He mentioned that this method can be used, or if there's an extension for the shallow water depths, or yeah. And another question is that how much would be the effect of the capturing the realistic weathered surface or curvature on the ship operating at the selected draft?
Yes, okay, Renato, thanks a lot for your question, okay? I can answer this one by one. So first one, extension to shallow or finite water depth. This is some ongoing work. So as I introduced already in this slide, I don't remember, okay, this must be slide 17. So actually, if you apply a different scheme to calculate this reflection coefficient, then trivially this eddy resistance in shallow water can be captured. So we have done this work. So you can see actually in this graph, the method is applicable. Okay, not this is empirical method. Okay, it is applicable to shallow water case as well. We are working on actually possibly extending this empirical approach to shallow water as well, because at least in sea trials, some area in let's say in Far East, where the ship trial often take place, the shallow water effect can be of interest. So this is the answer to the first question. We are working on that. Secondly, capturing the effect of realistic wetted surface of the ship operating at the selected draft. Indeed, if you as input to this method, we have actually draft at fore and draft at aft. Okay, so that being said, the impact of a draft change can be captured by this method. So, however, the accuracy, I don't know what kind of accuracy are you pursuing. That is some tricky point. Huh? as we said, at least for ships under ballast condition and volume carriers with very high B over T ratio, we compared with experimental data, and the agreement is very satisfactory. So I hope I answered your question.
Yes, thank you very much, Liu. And there is also one more question, and it is actually related to the applicability of the given method, but for bodies which are operating in a close proximity of the free surface with a forward speed. So up to now, of course, the formula is applicable to YTTC. I mean, we know for the free surface piercing bodies with a forward speed, like ships or something like that. But so what about the bodies which are operating in a close proximity of the free surface? So the bodies are submerged and they are operating in a wave field. So like for instance, you will have a submarine which is moving with a forward speed, but in a close proximity of the free surface. So the submarine is actually submerged. So what about that? Could you please comment?
Very interesting question. Okay. Today, okay, I presented the methodology, how we followed to develop this method.
Yeah.
So that is one reason we didn't just present the method, but instead we present how we developed the method. I think this kind of methodology can be explored by people who are working on specialized topics. However, in our case, you can see we don't have any data for submarine. We didn't have any input data for submarines. Okay, so I don't see how possible this method can be applied to submarines. But this methodology, maybe you can actually follow to develop some other formulas for your own interest.
Yeah, because I'm actually asking you this because a couple of years ago we investigated these kind of scenarios and so on, and then what you will be able to see from the investigation is actually that if you are going to increase the forward speed, and if you have a ship type of a body, then with increasing forward speed, of course, the resistance will decrease. But what is happening with the submarines type of body which are operating in a close proximity of the free surface with a forward speed, then with decreasing speed, actually the added resistance will go down.
Well, a lot of research.
But okay, this is just this is just my specialized type of a question. So of course, this is somehow extension of the
Yeah, we can discuss on that.
Yeah. Okay. Thank you very much. Thanks.
Thank you. Thank you.
And thank you, Renato, for very nice questions. Also, Professor Apostolo Papanicolaou also going to ask a question add a comment about submarine. Yeah, feel free to.
Yeah, thank you. I like these questions that come if we have not considered them. But so my response would be as following. Even the answer is not that is much easier. The submarine, because it is not surface piercing, it will be much easier to treat numerically. And then the points that we can generate in order to fit this empirical method will be, in lack of experimental physical experiments, will be numerical points. So that means that I can see that if somebody sits down, then can develop this with the approach that the general approach that Shukui presented, and then have the points, as I said, generated by numerical simulation. So the points that you need to fit the formula. the submarine hydrodynamics of submarine is much easier than for a ship. You know that it's a major issue. Also, a brief comment to the shallow water issue. This is tricky. It depends also on the speed of the ship, okay? Because you have there the interaction between the steady wave system that is interacting with the bottom, depending on the speed and the fluke number that is dependent on the water depth. And this interaction with the incoming wave that is also affected by the water depth creates some issues that are not easy to to treat. And we had in the Chopera project the colleagues from Belgium, the Hydrolab laboratory there. They did also experiments on this and found trends. There are some publications on this, and I think especially the colleagues from Belgium, they have contributed a lot to this subject, but it is tricky. If the speed is low, like in the minimum power regulations for DEI, then issues are different and maybe can be treated also easier. But as I said, attention should be paid. For zero speed or very, very low speed, Shukui has shown how to do that. It's not a big problem. Thank you.
Yes, thank you very much, Professor Papanicolaou. Yes, thank you.
Thank you.
Thank you very much for a very nice comment.
I mean, we like more people to know about this method. And also we have publications shared on a few platforms like ResearchGate. Okay, we cannot share it in public, but if you make a request, for sure we will share with you, okay? Not only these slides, but also the publications. For the public version of code, we do not have yet at hand, but we do have a version of Excel which was circulated to ITTC committee. So if you make a request, and we will assess that and reply to you.
Okay.
We can share that. Okay.
Okay. Yeah. Thank you again for a very nice presentation and your time. It was very, very informative and nice presentations. And also thank you all for attending this webinar. Yeah, thank you very much. It was our pleasure.
Thank you, Exxon, for inviting me, and it was really a pleasure of mine to share our research with people both from academia and the industry. We hope that if there is any question when doing research or implementing this method, please get in contact with me, and I will be very happy to support your applications. Thanks a lot.
And yeah, this is also, you can see the IMT webinar email here. So feel free to send me an email if you have any feedback or suggestion, or if you are also interested in having presentation through IMT webinar.